This is Mr. Lee. In this video, we are going to continue our series of finding E fields for different shapes, where Gauss's law doesn't quite cut it. In this video, we are going to be doing a charged half circle. All right, let's begin. So the first thing I want to do is draw a quick little sketch of a charged half circle. So let's draw our coordinate plane first. This will be our x-axis. This will be our y-axis. Let's draw a semicircle here, a semicircle there. Great, now we have a half circle. And we'll just call this half circle a positive Q half circle. Okay, so let's identify one. The reason why we can't use Gauss's law here is that the E field is not uniform if we enclose it. So for example, if we enclose the E field, I'm going to do this with the highlighter, right? If this is our E field, or if that's our Gaussian surface, you'll notice that everything within the E field is not uniform. Therefore, we cannot use Gauss's law. But fear not, it is a-okay. We can figure this out. So we're going to try to figure out the E field at the origin. So the first thing that we want to do is, one, take a look at our formula. Our formula says E is equal to KQ over R squared. And if you remember from the previous video, the method that we do is we take a look at tiny bits of charge. So if I were to take a chunk of this semicircle, okay, that is what we call our DQ. How is that tiny little chunk creating a tiny bit of a E field? And we call that our DE. So let's take a look. If we have a DQ here, and we are looking at the origin, that DQ will create an E field that emanates outward like so. All right. And from there, we could do a little dotted line so that you can see the path that it'll take. But at that point, the E field will go out like that. Now, for those of you that are pretty savvy with the physics, know as soon as we have angled forces, we need to break it up into its components. So here we have an angle that we call theta, and this is also an angle that we call theta. So we can actually break apart this DE into its x and y components, and I'll do that with my two different colors. Let's do blue. So we have here, this is my DEX, and I'll do another one in green. We can call this DEY. So we have DEX and we have DEY. All right, so all's right in the world. Cool. So if we go to the other side of the half circle and we take another chunk, okay, and so let's say it's like equidistant or equal angles apart, and we also call this DQ. That DQ will also create a E field that emanates out this way. We can also call that DE, where DE, because it's a angled force, we could break it apart into its two components. Here we have DEX, and of course the other side we have DEY. All right. Now, for those of you that are used to looking at components like this, immediately you'll notice something. Along the x-axis, our DEX and our DEX from both of our DQs, they're pointing in opposite directions. So what this means is that our x components from our DEs will cancel out, leaving us only with our DEYs. So in terms of physics, what this means, and of course in terms of calculus, is when we take the dq of this entire half circle, okay, when we take the dq of the entire half circle, all of the DEXs will cancel out, leaving us only with a net DEY, and we call that our E field. Yeah, let me make that a little bit better. We call all of the DEYs added up, we call that our net E field. So the idea here is that we use this idea called symmetry to make our math a little bit easier. Instead of having to find DEX and DEY, we only have to focus on the DEY portion because we know that all the DEXs, when they add up, it'll add up to 0. So only the DEYs actually matter here. Okay, and that symmetry will aid us with our calculus. So let's begin. Over here on the right, I'm going to do the calculus portion. Yeah, so we have our original formula. I'm going to write the calculus version here. We have dE is equal to k dq all over r squared, right? But here we get to do something special and unique. We know that we only care about dEy. So the next line down, I'm going to write the same thing, except I'm going to make sure that we have the y component. So this y component comes from the angle that we drew here. According to this angle, the y component is opposite of that angle. And remember our laws of sine, cosine, and tangent. Whenever you have something that is opposite, that is the sine of the angle. So we have dEy is equal to k dq over r squared sine of the angle. So what this shows us is if you're given this image here and they show you the angle, as advanced physicists as such as you will know that only the y component is the component that will add up because the x components will negate itself. Cool. All right, so there's a couple of things that we'll have to do in a little bit, but let's go through the thought process here. So if we integrate both sides, okay, if we integrate both sides, we get e ey is equal to, I'm going to take out all of the constants, k over r squared, the integral of dq sine of theta. Okay, so what we have to do now is we have to declare our bounds. If you remember from the previous video, we have to change up that dq. That dq is a problem for us, and you'll see why when we set the bounds. So the bounds that we're going to set here will come in terms of the angles. It goes from 0 all the way, because it's a half circle. Watch what I do here, because we want everything to be in terms of theta. It's going to be pi, because we know that 2 pi is a full circle. Okay, so for a half circle, it's from 0 to pi. So the next line that what I wanted to do is I want us to be able to replace that dq with something that we can actually use. So I'm going to leave the sine theta there. All right, off on the side here, let's redefine this, this dq. Okay, so here we have a linear line of charge, and this linear line of charge is dq, okay, over d theta. So what this shows us is that as our angle is changing, our amount of charge is also changing. So it's a ratio. And when we do the full half circle, we get q over pi, right? And so if we rearrange this, we get dq is equal to the total charge q over pi times d theta. And now here, our calculus brains are firing because we know that our bounds are in terms of theta, and here we have d theta. So what I'm going to do now is I'm going to substitute what we just found here into our dq there. So we get q over pi sine theta d theta. All right, next line down. So when we did that substitution, a couple of new things got introduced, mainly a couple of new constants. So one of the constants is this capital Q. Let's take that out over r squared. And of course, pi is also constant. Let's take that out. So our bounds is we are integrating from sine theta d theta, and our bounds are from 0 to pi. Okay, so when we take the integral of sine theta, we are left with negative, let's see, yeah, negative cosine of theta, where our bounds are from 0 to pi. And if we plug that in, we get negative, negative 1 minus, minus negative 1, minus negative 1. There we go. All right, there's a lot of negatives there, so I want to break this down. I'm going to highlight the negatives that come from that negative there. So that's a negative there, and that's a negative there. And this negative 1 that you see here, this is from cosine of pi. There we go. That's from cosine of pi. And this 1 right there, oh, why is it so big? That is from the cosine of 0. And this minus sign that we see right here, right? This minus sign, that's simply from subtracting the upper bound minus the lower bound. All right, so I broke that apart. There's a lot of negatives there, but as long as you're keeping everything straight, you should be fine. All right, so our final answer becomes k capital Q over r squared pi, and all that math in there simply turns out to be 2. So we get 2kq over r squared pi. And that is the E field at the origin for a half circle. See you next time. Bye-bye.